Hi, I'm Yun-Sung Lee from READ AI Research. Let's talk about our work towards practical plug-and-play diffusion models. Diffusion-based generative models have excelled in image generation, allowing external models to control the generation process without denoiser fine-tuning. Current issues include their inadequate performance with noise inputs and the need for fine-tuning using noise-corrupted label data. This method is limiting due to its difficulty with diverse noise levels and constraints on data collection for various tasks. We propose a strategy using multiple experts, each proficient with a specific noise range, to guide the diffusion process. Further, we present a practical plug-and-play PPAP framework which offers efficient fine-tuning and data-free knowledge transfer. PPAP guides diffusion successfully with fewer parameters and no label data, enabling various models to interact with publicly available glide in a plug-and-play manner. Now, let's explain our work in more detail. In classifier guidance, user intention is given with a specific class. For example, a crawl leaf. If we have an image classifier which can handle those images in diffusion process, we can guide the diffusion denoiser model with the gradient of the classifier. Though, there are many other user intentions that users want to guide besides class. Thus, we extend classifier guidance to any other user intentions with off-the-shelf models, like DimLab Breeze segmentation model, LesNet classification model, Midas depth estimation model. What's more, PPAP is even possible with pre-trained diffusion models trained on unreleased datasets. Let me explain the problems we solved to achieve this. What if we took an off-the-shelf model and turned it into a guidance model? As you can see in the image on the far right, guidance via the naive off-the-shelf model fails. But why? This is because diffusion models receive noisy images as input during the reverse process, while off-the-shelf models have never been trained on such images. That's why guided diffusion trained the classifier model with sampled images in diffusion process. However, the guidance of fine-tuned classifier on a noisy image is still poor, because it has two limitations. First, performing on inputs with extremely various noises is too hard for a single guidance model. Second, it requires a label dataset which hinders scaling up for various tasks. We aim to overcome these limitations in two ways. First, we introduce a multi-expert strategy. Second, we introduce a practical framework that leverages parameter efficient fine-tuning and data-free knowledge transfer. Let's start with the details of the multi-expert strategy. In multi-expert strategy, each expert guidance model is fine-tuned to specialize in a specific noise range. In the reverse process with guidance, the guidance gradient is given by the expert in charge for each time step. As a result, we can see that the time step specific confidence of the guidance model also improves significantly. We can see the confidence of the single fine-tuned classifier drops for cleaner images, which is highly influential to the quality of the image generation of the diffusion model, while the multi-experts do not. This image shows the results generated by different comparison models for the class Husky. As I say at the beginning, we want to extend classifier guidance to any other user intentions on pre-trained diffusion models, even if it is trained on unreleased dataset. However, whenever applying a new off-the-shelf model, the multi-expert strategy must utilize multiple networks and collect the label dataset. These two limitations hinders the scalability of guidance. Therefore, we solve the problem of handling multiple networks with a parameter efficient fine-tuning scheme, and the problem of collecting label datasets with a data-free knowledge transfer scheme. To reduce the number of parameters to fine-tune in multi-expert strategy, we only fine-tune a small number of parameters while reusing most of the frozen off-the-shelf model. Specifically, we fine-tune bias and batch norm and apply RORA, row rank adaptation. Meanwhile, the dependence on a level dataset is mitigated by data-free knowledge transfer. First, a clean dataset is generated unconditionally by a simple diffusion model, and then an off-the-shelf model is trained so that its predictions on the noisy image mimic those on the clean image. Finally, the combination of parameter-efficient fine-tuning and data-free knowledge transfer in the multi-expert guidance results in practical plug-and-play, or PPAP for short. Now, let's show some experimental results. There are the results of class guidance on the ImageNet dataset. The multi-expert strategy is the most powerful, and PPAP is scalable for practical cases, but also powerful enough. Both are our novel method. Both are generalizable across samplers and architectures. It's also worth noting that PPAP was only trained on a generated dataset with no supervision. Here are some qualitative results from the ImageNet classifier guidance. Compared to multi-experts, we can see that PPAP has a surprisingly high quality of generation. Given that the number of parameters learned by PPAP is 5.72% of the size of multi-experts, and the training was done on a unleveled dataset with about half as many images. Now, let's extend PPAP with various user intentions. To verify our practicality claim, we use GLIDE as our target diffusion model, where the training dataset is early released and only the model weights for inference are public. We utilize the less than 50 model for class guidance, the BindUs model for guidance via depth map, and the DIMLab V3 model for guidance via semantic segmentation map. Here are the results of guiding GLIDE with ResNet 50. Notably, our methods can semantically guide the GLIDE with varying styles of images, such as cartoon-style images, which is interesting because ResNet 50 has never seen cartoon-style images in the ImageNet. PPAP can obtain both the generalization ability of GLIDE in various domains and the semantic understanding ability of ResNet 50. Here are the results of guiding GLIDE with MyDice. The correspondence between the depth map and the generated images is well matched. Finally, here are the results of guiding GLIDE with DIMLab V3. Again, we see a well-matched correspondence between the segmentation map and the generated image. Thank you for listening.
Thank you.